Hey, good afternoon. This is Celso Batalha, Astro 10, and I know you guys might be busy since, if I'm not mistaken, today there is an exam going on, and it's a second chance for midterm number two. So I hope you remember that, and I will send an email to the entire class in a little bit, so that if you are not done, you still have time to do it. In case you're listening to this before doing the exam, I recommend that you do it because the system will, or I will collect the highest score of the two attempts. So today we are initiating star formation ideas and basically advancing to a full explanation of what HR diagrams are, Hertzsprung-Russell diagrams are, is one of the key aspects of our courses. Remember, when we initiated our courses, we knew stars existed. We all know stars are out there. One thing is to think of stars as being some dots of light out there in the sky that you can see, throughout the year. Some of them and some others you can see on particular weeks or months of the year. And then you don't see them anymore. And then the first few days of class, we learn we don't see them all the time because Earth revolves around the sun, right? So in certain months of the year, we can see certain constellations. We don't see in others because Earth is occupying a different position in space and around the sun. Now, what we haven't discussed yet, how the stars evolve. I mean, yesterday, in fact, in fact, 2 days ago and yesterday, we talked about how stars formed. And that was one of the major discussions we just had. So stars are formed as long as you have gas in the interstellar medium, but not only that, as long as you have also gas with a certain density, with a certain mass content. Because if you do, then gravity, and most of you discuss that, and then gravity will slowly take it over and pull this gas into a point called center of mass. Now, if you also have a rotation, and these giant molecular clouds, they do have rotation, they do have this initial spin. Once contraction takes place, the clumps, the gas that will eventually form a star, initiate a rotation faster and faster as contraction takes place. It is the ballerina effect your book mentions and talks about. And so this contraction and rotation keeps taking place to a point that a bright central star is formed and a circumstellar disk around the equatorial plane of the star is also formed as a result of this initial rotation. Out of this circumstellar circumstellar disk, planets will form in a process pretty much similar to the one that formed stars, and to the point that eventually gravity will drag contraction to a protoplanetary disk. So we kind of went through these steps and you guys discussed that. I think we are all okay with that. Now, as the star keeps contracting and reducing its volume, eventually the core of the star, about 20% of its radius, becomes dense and hot enough to ignite fusion reactions, thermonuclear reactions. So when this time arrives, now there is another player in the energetic budget, of the star, and that is as fusion reaction takes place in the core of the star, energy is released, and that energy helps the star to become stable. So the star stops its contraction, but also that excess of energy that comes from the core will not expand the star. So it gets to a point the star becomes stable with a perfect balance between two forces, the inward force we call gravity and the outward force which is provided by gas pressure. And this gas pressure is maintained because heat is coming out of the central core of the star, again as a result of fusion reaction. So now today we are trying to tackle the following questions. Well, fusion reactions occur because the core has hydrogen atoms, right? And by the way, let me show you, these pictures here are pictures of regions of star formation. All these clouds, they are not like the clouds in our atmosphere, which are much denser than those ones. Those clouds are called giant molecular clouds, and when gravity takes over, little dots in these clouds we call clumps will give rise to star formation. In this picture, you see an interesting thing, and that is these stars are Orion stars. In fact, this constellation is Orion, the one you're seeing right here. But if you had infrared eyes or infrared detector, what you would see is not just an empty space with some stars in it, but a large display of gas, cold gas, in fact. And again, this is the hallmark of star formation. You gotta have cold gas. If the gas is cold, gravity will be able to clump and bring gas into a central part, which will eventually give rise to fusion reactions in the case of a normal star. So more of the nebula, in this case, is Orion Nebula. Orion Nebula is right here. See this little thing, this little fuzzy thing in there? This is where Orion Nebula is located, and then you can expand it, and then you can see this type of things here. So more nebulosity. So the main point is stars are formed out of gas and dust, and if there are a large stretch of gas, associations can be formed. And in this picture, you see an example of OB associations. So what are those? In OB associations is when gravity takes over and start forming several sibling stars in a given location. And this we are going to learn, in fact, today. The faster the evolution takes place in this contraction moment, the faster it takes place is the result of the initial mass of that cloud. So more massive clouds contract faster than those that are not as massive. In other words, and this is very important, evolution or stellar evolution is governed by stellar mass. So the most massive stars are those that evolve faster. Those less massive stars are those who takes longer to complete their evolutionary cycle. So if you have a cloud that fragments into smaller clumps that will give rise to stars, and assuming all these clumps, they have different initial mass, those clumps that are more massive, they will undergo their evolutionary stages or go through the evolutionary stages faster than those clumps or low mass star. So in other words, if you have a bunch of sibling stars recently formed, the heavier ones, the more massive ones, and they are the OB stars, they will go faster through their evolutionary cycle and eventually explode in supernova. So O stars are massive, and their end of life is a majestic explosion called supernova, which I will discuss tomorrow. But low mass stars, they don't explode unless they are in a binary system, but that's a detail. Now, once the explosion takes place, the explosion sets in motion a shock waves, and the shock waves, the propagation of it, helps to form more stars. And that's what you see in this OB association. So every now and then you find clumps of stars that were formed, in fact, by the passage of shock waves through highly dense gas. Now, here is a rendering of the last stage of stellar formation, and this is what we talked about yesterday. You have a major clump. The clump contracts and rotation gives rise to the circumstellar disk, and then bipolar flow comes out as a result of conservation of angular momentum, and eventually you have a central star with a circumstellar disk. And here are real pictures of stars, young stars with a bipolar flow. And this type of stars are called H-R Herbig-Haro objects, HH objects. And then you can see them all. Okay. So let's go to the next slides in today's series. Oops, somebody in there. Let's see who it is. I don't know. How do I go? Where do I go? Where do I go? Thought it was somebody there. Okay, so let's go to the next slide. And that is basically how they evolve. So when it gets to the point, the star is able to steadily produce energy out of the fusion reactions, the 4 atoms of hydrogen being converted into 1 atom of helium, and then gamma rays are produced, and these gamma rays are pretty much light, energetic light, that propagates through the central star, and that energy is imparted to the gas that helps to keep the star stable for a long time. So most of the lifetime of the star will be in that phase, just burning hydrogen and helium and releasing optical light. So that's where the sun is at. The sun is what we call main sequence star that is undergoing this fusion process and is relatively stable. But the amount of hydrogen in the stellar core keeps being depleted as these fusion reactions takes place. Just for comparison, the sun now is about 60, the sun's core now is about 60% of a helium core. And that's what you see in this picture right here. In this picture, you have a main sequence star that has a hydrogen burning core, and surrounding that, the stellar regions overlying the core. Now, eventually, this hydrogen is going to be depleted, and the core is going to be a helium core. When that stage arrives, the star ceases to be a main sequence star. The star is not a main sequence anymore, and then goes on to be what we call a giant star. And let me show you in this diagram what I mean. So this line over here is a line that locates, is a locale where stars are currently undergoing this process of fusion reaction, the hydrogen into helium in the core. And this is the so-called HR diagram, Hertzsprung-Russell diagram. When you plot the stars following their luminosity and their surface temperature, so see surface temperature in the x-axis and luminosity or intrinsic energy in the y-axis, when you plot that information of all the stars we know, what we find is 90% or more of the stars happen to be located in this region we call main sequence, where the sun is right now. But eventually that the star will be depleted, completely depleted of hydrogen in the core. And then changes happen. And there are two significant changes in the star. First, and that is important, because of fusion reactions is finished in the core will contract. The core will slowly shrink under the weight of the overlying regions, under the weight of the star itself. So just imagine the core of the star that is supporting the weight of the star. Suddenly that core has no more energy production because fusion is gone. It's a core of helium, and as a result this core starts to be shrinked because the overlying layers are able to push it in. Now, one of the laws of nature in thermodynamics is if you take a gas and you contract the gas heats up because you are forcing the elements that make up the gas to collide more efficiently among themselves. And collision in science means rising temperature. So you have heat being produced. So in other words, as the core shrink, heat is produced in the core and the temperature in the core rises. So when the sun was a main sequence, when the star is a main sequence, the core was about 15, 20 million Kelvin. But when the core starts to heat up, the temperature increases up to a point where it reached the level of 100 million Kelvin. And then another stage would be initiated. But before we reach that stage where the fusion reactions again will be ignited in the core at 100 million Kelvin. So during that stage, again, the core is contracting, the temperature is rising, and as shown in this figure here, the region underlying the core is kind of a bluish here, right? The helium core is bluish, and the picture is small. Let's see if I can expand it. So it's a helium core, it's small, but in the region surrounding the core, now we have what is called the burning shell, hydrogen burning shell. Fusion reactions are happening not in the core, but in the region overlying the core. As a result of these fusion reactions, and as a result of this addition of more thermal energy coming out of this helium core, since the temperature is growing, more energy comes out together from this central region. And this excess of energy produce an imbalance in the star. The star starts to expand. And we call that stellar phase a red giant. So a red giant is a phase in which the core is contracting and heating up, and the outer layers are expanding in response to the excess of energy that comes out of the core. Okay. Now, eventually the core becomes so hot that, as I mentioned before, that helium fusion reactions take place. It's called triple alpha process. And these helium fusion reactions will give rise to carbon and oxygen, so other atoms. So fusion reactions is a process by which heavier atoms are produced as a result of the merging or fusion of lighter type of atoms. If you go to your atomic table, you can see the first one, the lighter one, is hydrogen, and then helium is the next one. So take 4 atoms of hydrogen, and then you can fuse into 1 helium, and take the helium through a complicated process. In fact, was the astronomer Fred Hoyle, the one who was able to figure out the triple alpha process operating in stars. Then you can reach and form a carbon atom. And so eventually, the core is, when the core initiates its fusion reactions, initiates in a very short amount of time. It's called flash, or helium flash, where the entire core, helium core, initiates fusion reactions, and then the helium slowly initiates its conversion or its fusion into the heavier carbon and oxygen. So at that phase, the star again experiences some moments of stability because a steady flow of energy comes out of the core, and the star is said to be occupying the horizontal branch in the HR diagram. Now, eventually, the core of carbon and oxygen cannot be fused anymore in low mass stars. Tomorrow I will talk about high mass stars, and the star undergo a last stage in its evolution, where the core, now a carbon core, contracts slowly, gets hot. Helium fusion shell and hydrogen fusion shell surround this core, producing some fantastic excess of emission, and the star becomes an asymptotic giant branch star, which you can see in this picture here related. And the final stage, the final evolutionary stage of a low mass star occurs when the core itself is able to divest from all the overlying layers. And by expelling these overlying layers, what we observe is a system we call planetary nebula. And that is the end of stage for a star like our sun, a low mass star like our sun. Here in these pictures is indicated how can we learn if we study several stars of a given group of siblings. By studying them, we can find how old that group of stars are, because we can trace exactly the moment in which they leave the main sequence. So those are the main points in the evolution of a low mass star. And tomorrow I will go over the main points in the evolution of a high mass star. So let me go to the chat room. I don't have anybody there, I don't think so. Okay. All right.